myself Prachi Agarwal, Assistant Professor in Ajay Kumar Garg Engineering College in the Department of Electronics and Communication. The topic for my lecture is deposition process. And this I will be covering chemical vapor deposition, atmospheric pressure CVD, low pressure CVD, plasma enhanced CVD, and physical vapor deposition, evaporation and sputtering. So first of all is chemical vapor deposition. The deposition is the creating a layer on a substrate is basically a deposition. So deposition can be done using two methods: chemical vapor deposition and physical vapor deposition. So first, in chemical vapor deposition, the first one is atmospheric pressure chemical vapor deposition. In this, basically, this is the basic diagram of this type of CVD. This is a heater. The heater is placed inside a belt. The belt is a conveyor belt, and on the conveyor belt these are wafers. The wafers are kept on it, and the temperature of this belt is at very high temperature. So from above we are using some kinds of gases like nitrogen gas. We are adding into the substrate so that the temperature can be maintained, as we are providing high temperature from the heater. So we are providing some cool gases from it so that we can get a vapor, and the vapors can be collected and can be deposited on the basically the wafer. So in this atmospheric pressure CVD, it works at atmospheric pressure. That means we are not requiring any other kind of we are not creating any other kind of pressure. It totally works on the atmospheric pressure. It is used to deposit a layer of material, typically severe micrometers thick, onto a wafer or other type of substrate. So basically it is used to deposit a layer of material which is basically a micrometer thick, and we can provide a deposition onto a basically a wafer. So it is also used as surface finishing process for items such as tools and turbine blades. These are the application of such type of basically methods. So this atmospheric CVD method has inherently poor utilization, and it is extremely susceptible to oxidation due to greater gas density and residence times. So these are the advantages of such type of method. First one is low cost. So atmospheric pressure CVD is a low cost basically method, because it is not requiring any kind of extra development, extra process for creating the pressure or something. It is utilizing only the atmospheric pressure, and it can be less expensive than vacuum processing, because it does not require the same structural strength or pumping system. It is not requiring extra kind of pumping system which we are requiring in the other methods, which I am going to explain. And because there we have to maintain the pressure into that vacuum chamber, right? So next, first one is low cost, second one is uniformity, and then we have economic performance. So economic performance means that APCVD can be economically efficient for various applications such as solar cell manufacturing. So for the application of solar cell manufacturing, this APCVD is quite applicable, and we can utilize it due to its low cost and its uniform layer structure. The disadvantage of APCVD is it has higher surface roughness. Sometimes it provides some kind of roughness, so this is a disadvantage of APCVD. And also the temperature limitations are there, that it may be suitable for atmospheric pressure, but temperature we have to take care in this particular system. And contamination risk is also there, as there is no vacuum, there is no there is no such kind of chamber, so there may be a chances of contamination. Application of APCVD is for the deposition of silicon dioxide. So there is a topic where you have to write about deposition of silicon dioxide, deposition of polysilicon. So when such type of question will ask that explain the deposition of silicon dioxide, then you have to explain basically APCVD, because APCVD is suitable and it is utilized for the deposition of silicon dioxide. Now another CVD method is low pressure CVD, low pressure chemical vapor deposition. That means in this the wafer is placed vertically. Here you can see these are the wafers. The wafers are placed vertically, and these wafers are maintained in a quartz tube. The wafers are placed, and the temperature and the pressure of whole this structure is maintained by pressure sensor. So pressure sensor is basically used to maintain the pressure inside it, because it is a low pressure CVD. And the samples is basically for wafers. This is a 3-zone furnace. So furnace is basically the structure we are utilizing to keeping the different wafers, right? And the gas is inlet from this, the gas is going from it, and the particular, it is condensing and creating some kind of wafers, and that can be collected over your wafers. Okay, so there is vapor. Vapor is something which which you have studied for water vapor or something, some kind of vapor. And the vapor is the thing, the you can say the part of substrate which you have studied, which I have already explained you while giving my lecture on wafer making, right? So wafer is basically the making of silicon wafer from the substrate, from the big substrate, right? So these are the wafers, and the vapor is going to deposit on this wafer. Now, advantage of LPCVD: uniformity of thickness. Basically, it provides uniform structure, high reliability, better homogeneity of deposit layer. It is basically the same, that uniform and the homogeneous structure it provides, and high reproducibility. That means the such type of method is quite usable in industry, because it is having lots of advantage as compared to the previous method. And disadvantage of this is lower deposition rate, since in this structure, in this method, we have to maintain the pressure, right? So that is a constant which we need to take care among while using this. So this creates a low deposition rate. Then APCVD: high temperatures needed for the process. We are requiring high temperature in this, and also it should be handled properly, right? So these are the advantage of LPCVD and the disadvantages of LPCVD. Now, applications of LPCVD: it is used for the deposition of polysilicon and silicon nitride. So earlier APCVD was used for deposition of silicon dioxide, but this is used for the deposition of polysilicon and the silicon nitride. So these are the three topics, that deposition of silicon dioxide, deposition of polysilicon, and deposition of silicon nitride. So we can we can write over these topics by giving these diagrams and by explaining these basically methods on this. So the third one is the third method from the chemical vapor deposition is plasma enhanced LPCVD. In this plasma enhanced CVD, basically plasma is generated using the electric field to create energetic plasma that activates the CVD reaction. Basically, the plasma is generated by using the electrodes, and that plasma is utilized to creating the layer over the substrate, over the wafer. So here the wafers are kept in this this chamber, and this is heated sample holder, and the pump is used to take out your wafers. The gas is going from this side, from both the side, gas is going over the wafers, and the whole process is using the glass cylinder which I have utilized and which I have written, and the insulated RF input. Input is used just to create the basically the electric field and the electric current which is developing the plasma, and that plasma is going to create a layer on your wafer, right? So this is plasma enhanced LPCVD. So plasma enhanced low pressure CVD is another method of chemical vapor deposition. So advantage of PECVD is it offers lower deposition temperatures. The rate is quite lower as compared to other method. Why? Because it is having a fixed structure. This is the holder on which we are keeping the wafers. So this structure is quite fixed. So limited amount of wafers can be kept over it, so that this provide a limited deposition, and limited wafers can be utilized by this method, right? So it basically offers lower deposition temperatures. It has good conformity and step coverage on uneven surfaces. It possesses tighter control of the thin film process since it is a plasma method. So in this basically process, the deposition is quite controlled as compared to the other method, and it is having the high deposition rates. So deposition rate is again high because we are using the plasma here, and so that we are having a uniform structure over the wafer. And on the disadvantages part of this, we are having substrate damage. The substrate can be damaged by ions and contaminations from the electrodes, since in this methods we are using electrodes and this electrode is basically creating some kind of plasma, and this plasma we are utilizing over our substrate, right? So these electrodes, these are electrodes. So if these electrodes got damaged, then whole system will get the whole system will get error, and we are not getting any kind of plasma, and that is why there is no deposition over it. So this is in this disadvantage we can write this is substrate damage. That means substrate can be damaged by ions and contamination from the electrodes. When these electrodes are not properly working, they contaminate our wafers, and the whole process whole process will get vanished out, right? Next is process control. The process can be difficult to control because this whole process is electrically conducted. So in this, some kind of electric field is also generated, so it is quite difficult to control this method as compared to LPCVD and the APCVD. So next is production efficiency. The production efficiency is also low in this because I have told that this is the particular this is the, you can say, the table on which the wafers are kept. This is the holder basically. So limited space are there. So for this limited space, the production is quite low as compared to other methods. So cost, PECVD can be expensive. This is expensive method because it is utilizing electrodes, and it may be utilize some kind of other things to create the electric field. So it is an expensive method. Barrier performance. The barrier performance is weaker than Perlin and depends on the thickness, layer count and plasma type, right? So these are the some disadvantage of PECVD. Applications of PECVD. It is used for deposition of silicon nitride and the deposition of silicon dioxide. So we have seen that silicon dioxide can be used by one method that I have told earlier, APCVD, and silicon nitride can also be created by using LPCVD. So PECVD is used for the deposition of these two things like silicon nitride and silicon dioxide. So let me just tell you about these methods, these polysilicon, silicon nitride and silicon dioxide in short. So first of all, deposition of polysilicon. Polysilicon is basically used in most devices. It can be used in for transistors just to create the, you can say, the ohmic contacts. So such polysilicon deposition is quite important. So this polysilicon deposition is created done by the APCVD method. So in this, what is happening basically, this you have heard about silane, SiH4. This SiH4 is heated, and this process is basically, we can say that, pyrolyzing silane between 575 to 650 degrees Celsius in a low pressure reactor. We have to use this, and this will create this silicon and the H2. Silicon and H2 will get released. This process, pyrolysis process, is known as, basically, it decomposes through heating at high temperature. So when we heat silane at certain temperature, it gives Si and the hydrogen. So this is basically the deposition of polysilicon. And silicon, we all know that it is a chemical compound, and it is composed of silicon and hydrogen atoms, that is SiH4, right? So I have written it can be done using basically LPCVD. So this is the graph which I have shown. So in the graph, this is basically the silane partial pressure which I have plotted on the x-axis, and on the y-axis I have created the deposition rate. So what is this showing? This is showing a non-linear structure, and in this when the temperature is increasing, the deposition rate is also going to increase, and it is showing that how the silane is going to change over the temperature, right? So now another one is deposition of silicon dioxide. We all know, we have studied the oxidation part, in which oxidation we are creating the silicon dioxide. But here the deposition of silicon dioxide means that we are using silane SiH4, and on this we are adding some kind of nitrous oxide N2O, and at the temperature 200 degrees Celsius, which is basically a argon plasma temperature, and it gives SiO2. So here the SiO2 layer is formed by reacting silane with N2O, that is nitrous oxide, and it will give SiO2 and this H2 and 4N2. These are the products, byproducts of it. So when suppose this silane is not present, right? So in the absence of silane, we can get SiO2 by just in the absence of this nitrous oxide, we can get SiO2 by just reacting silane with oxygen. So we are reacting silane with oxygen, and here at 450 degrees Celsius, and we are getting SiO2 plus H2O. So this can be done using LPCVD and APCVD, right? Now deposition of silicon nitride. Silicon nitride is basically a chemical compound which is made up of silicon and nitrogen, that is Si3N4. It is also called trisilicon tetranitride. It is the most thermodynamically stable and commercially important of the silicon nitrides, and term as silicon nitride commonly referred to this specific composition, right? Due to this specific composition, it is called silicon nitride, and this is basically having a white high melting point solid. That means we can say that it is relatively inert, and it can be attacked by, if we use certain chemicals like hydrofluoric acid, or we can use, I have written the hydrofluoric, and or we can use some kind of H3PO4. So this is a highly inert gas, and it is very hard, around 8.5 on the Mohs scale, right? It has high thermal stability with strong optical non-linearities for all optical applications. So this deposition of silicon nitride is important for the optical purpose, and it can be done using LPCVD and PECVD. So I have already explained LPCVD and PECVD. So this deposition of silicon nitride we can get by using these two processes, right? Now another method is physical vapor deposition. Like deposition I have told done by two methods, chemical vapor deposition and the physical vapor deposition. In the chemical vapor deposition, we have seen that we are using certain chemicals to create the layers, to create the vapor and to get a deposit on the wafer, right? But in the physical vapor deposition, it is basically, here also we are creating a layer on the substrate, on the wafer, but in this the deposition can be done by using some physical methods. So there is no chemical we are using here. So, and this, first of all, the PVD method is basically of two types, evaporation and the sputtering, which I have already written in the starting. So in this basically what is basically happening is, in both the cases, formation of deposit on a substrate away from the source consists of following three steps. That means in evaporation and sputtering, these three steps are basically happening. That means converting the condensed phase, generally a solid, into a gaseous or vapor phase. That means we are creating a condensed phase, a solid, into a vapor phase, right? So how we are creating? We are transporting this gaseous phase. Then the gaseous phase which we are creating here is transported from source to the substrate, right? Suppose this is a source. So first of all, we have created the wafer from it, and those wafer are going to be used on a substrate, right? So here it is happening like this. Now condensing the gaseous content on the substrate. Now this is basically the substrate. This is the solid thing. From this you can say the wafers are coming. Now these wafers are coming. Now they need to be settled to create a layer. So this is all happening on this process, that is evaporation, right? So I have written the condensing the gaseous content on the substrate, followed by nucleation and the growth of film. So this is the thermal evaporator unit in which basically evaporation is happening. What is there is a evaporation source. Some source is used here. The tungsten is basically used, and there are some heaters, and this whole is happening in a bell jar that is of quartz or stainless steel, right? And in this bell jar, basically this is the source which is kept here, and the high temperature, high vacuum pumps are used, which is having around such values like 5 into 10 to the power minus 4 minus 5 torr to 1 into 10 to the power minus 5 torr, right? So this this bell jar is maintained at this particular values, at particular pressure, and tungsten is used. Basically the heater is used, and after using this we are having some kind of vapors, and these vapors get deposited over this wafers. So the wafers are kept here. So this is a planetary wafer holder. So this is a thermal evaporator unit. That means that we are creating some kind of vapor, and those vapors will be depositing over your wafers. Wafers are there, placed over the planetary wafer holder, right? Now another one is sputtering. Sputtering is the method. Basically in this there is some kind of thing, and on this particular thing we are targeting this by some kind of energy atoms, right? So on this, when we are targeting this, the main actual atoms of this will get come out from it, and they will get settled over the substrate. So this is sputtering. That means there is a source. On this source some kind of atoms are there, and you are hitting some kind of high energy ions you are bombarding. Now on bombardment, these atoms will come over your substrate, and they will create a layer. So this is called sputtering. I have written it is a PVD process in which ejection of atoms occur from a solid target by high energy bombardment. These atoms are then condensed on the substrate to form a film, right? And this is a well controlled method, as evaporation is not well controlled. We all know that when the particular element or particular source is heated, it will create a vapor, and those vapor will they cannot be controlled. As soon as that process gets stopped, then only the vapor will get stopped. Otherwise it is not a controlled process. But here it is a controlled process, that accordingly we can utilize it, and these are generally applicable to materials like metals, alloys, semiconductors and insulators. So argon is a rare gas element which we are using sputtering, and this whole process can be done using radio frequency, AC and DC magnetron sputtering, right? So this is the diagram of it. Like we are using argon. I have told the argon is the high energy ion. Basically it is used to bombard this, and this is a target on which some atoms are already placed. So when you are bombarding this by argon ions, the actual atom will fall over your substrate. So when these atoms were falling on this substrate, on your wafer, they will create a layer, and like this we are having a deposition over the substrate, over the wafer, and this is known as basically sputter deposition process. So I think now you can answer LPCVD, atmospheric CVD, plasma enhanced CVD, deposition of polysilicon, silicon dioxide, silicon nitride, and evaporation and sputtering. Although in the deposition of polysilicon, silicon dioxide and silicon nitride, there are lot other things which we can which we have to write and which we can quote, but due to the I have quoted here some brief only over it. So I think these things are clear to you. So thank you and Jai Hind.